Okay, let's talk about an optimization problem that we can understand geometrically. This is how to find the point on a line closest to a given point. So by way of example, find the point on the line y is equal to x minus 1 that is closest to the given point 1, 1. And so we're going to use our usual way of approaching things. You draw names for, and of course this should say min, because we're trying to minimize the distance here. Okay, let's start with you. This is understanding. So what's known and unknown? So we know the line equation, okay, and the point, okay. Unknown is distance and the point on the line. So let's try to draw a picture. So we have y versus x, and we're going to put the point minus 1 there and 1 there. Okay, this is y is equal to x minus 1, and we have the point 1, 1. This is the given point. And what we'd like to do is to find the point on the line which is closest to the given point. And so we need to have a name for the distance between the line and the given point. And so we'll call that d of x and y. So the distance between the line and the given point. Okay, so what's the formula for distance? Suppose we want to know the distance between x, y, and say x1, y1. That would be d is equal to x minus x1 squared plus y minus y1 squared square root. This is the distance formula. And so we would like to minimize the distance. We also have the formula for the line, and that is y is equal to x minus 1. And this describes the relationship between y and x. So let's think about how to minimize the distance. And here, there's a little trick we can do to make life a little bit easier. And so we're going to do that right here. So if the distance is minimized, then so is q, which we're going to call d squared, which will be x minus x1 squared plus y minus y1 squared. So we've gotten rid of that pesky square root sign. That helps a little bit. So let's write out what it is. Okay, so this is going to be x minus, now x1 is going to be 1, and y1 will be 1. This is the given point. So we have x minus 1 squared plus y minus 1 squared. Now we can substitute in for y, and so this is equal to x minus 1 squared plus x minus 1 minus 1 all squared. And so that's where we use the fact that the point is on the line. So we can expand this out if we want to. So this is x squared minus 2x plus 1 plus x minus 2 squared. And so this will be equal to x squared minus 2x plus 1 plus x squared minus 4x plus 4. And so if we group the terms together, we'll get that this is equal to 2x squared minus 6x plus 5. And that's our formula. We want to choose x so as to minimize 2x squared minus 6x plus 5. And so we're going to proceed to look for a critical number, because that could give us the minimum. And because this is a polynomial, the derivative exists everywhere, so the critical number will be where q prime of x is equal to 0. So 0 is equal to q prime of x, and this will be 4x minus 6. And if we solve this for x, we get 4x is equal to 6, or x is equal to 6 over 4, which is equal to 3 over 2. Let's double check to see that this is actually a minimum. So what we can do is check the second derivative for q. So q double prime of x is equal to 4, which is bigger than 0. And so that means that the shape of q is a happy face, because the second derivative is positive, and so the critical point is indeed a minimum. So x is equal to 3 over 2 gives a minimum for q. We can also work out the y value from the formula y is equal to x minus 1. So y is equal to x minus 1, which will be equal to 3 over 2 minus 1, which is 1/2. So x is 3 over 2, y is 1/2, is the point on the line which is closest to the given point, 1, 1. So we can go back to the graph and look at what this means. This is a line, y is equal to x minus 1, and we found the point on that line that's closest to 1, 1. The coordinates of that point are 3 over 2, 1/2. So we use this minimization method to deduce that.